All right, let's take a little closer look at the structure of the stomach, and we'll highlight some of the things that we said on the general overview of the digestive system. So the stomach actually it's a sac-like structure, and it actually has 3 layers of muscle. We have the muscles essentially oriented in different planes. So you have essentially perpendicular, parallel, and then we have oblique muscles. So these muscles allow for this churning that we think about that needs to happen in our stomach. So having the muscles go in 3 dimensions essentially are going to churn our food with the stomach acids, which also include we have enzymes to begin the digestion of proteins. Now, what they're showing us here are the gastric pits and the gastric glands and cells that secrete the gastric juice. So this is all super important because it's going to kill materials coming into our food, but it's also going to enhance the breakdown of our macromolecules. As the stomach churns, essentially it is going to be moving the bolus along, and then it's going to exit here at the duodenum, and we are going to have the production of what we call chyme at that point. Okay. Gastric glands, making the gastric juice. Yes, in fact, it has that enzyme I mentioned before, pepsin. Digests proteins, breaks them down into peptides or shorter pieces of proteins. They're not big and they're not the basic building block amino acids yet. We also know that those gastric glands are making that hydrochloric acid, which is lowering the pH of the stomach. And notice it also is going to activate that pepsin. So pepsin works best at a lower pH. And we know this when we do this in a lab. We can set up an experiment and it works beautifully. But if you don't have that lower pH, digestion takes a really long time to take place. There's also mucus in the stomach, really helping protect the stomach lining from the gastric juice that it's making, which is pretty interesting. So the stomach is going to spend about 2 to 6 hours forming that chyme and moving that food along into the small intestine. Now you're going to see throughout this chapter terms like sphincter. So essentially this is a round piece of muscle or a circular piece of muscle that's going to control the movement of materials from one organ to the next. So we have a sphincter at the base of our esophagus, between the esophagus and the stomach. Now we have another sphincter between the stomach and the small intestine. So essentially what it's going to do is just allow a small amount of chyme to enter the small intestine at a time. All right, so we have the small intestine, we have the duodenum, which is the first part, the jejunum is the middle part, and then the ileum, which I think I misspoke when I talked about the duodenum emptying into the ascending colon. It's the ileum that meets the ascending colon at the appendix. Okay, so let's talk about the digestive enzymes in the small intestine. So we know that the pancreas is really helping out a lot because it's secreting digestive enzymes, which include 2 big ones, pancreatic amylase, pancreatic lipase, and then we also have protease. So amylase is the pancreatic amylase is going to break down the maltose into basic subunits of glucose. The protease is going to break down proteins. Are really thinking about those peptides from the stomach now being completely digested into amino acids. And then we have lipase, also made by the pancreas, that is going to break down our lipids into glycerol and fatty acids. Now, as you might know, fats do not like to mix with water. So when I make a homemade oil and vinegar dressing, you've got the vinegar on top, you got this oil, and I'm shaking and shaking and shaking, and it never really suspends. I mean, it will for 5 seconds, and then it's already separating again. So the thing that we need for salad dressing and the thing that we need to fully break down our lipids is something called bile salts or bile. Okay. In our salad dressings, we're not going to use bile salts, but we're going to use other emulsifiers that are going to allow for those lipids to freely suspend in a solution. So our pancreas is going, our liver is going to make bile. The bile is going to be stored in the gallbladder. The gallbladder is going to drip out this bile or bile salts into the small intestine, and those bile salts in coordination with the lipase is going to essentially freely suspend the fatty acids in the solution, so essentially into droplets, and then the pancreatic lipase can break down those droplets finally into fatty acids and glycerol. Okay, so pretty neat. Now the small intestine is not acidic. In fact, it is a higher than neutral pH, and so we say that it's basic. The sodium bicarbonate in the small intestine is higher than neutral, and it's going to essentially need to be higher so it can neutralize that acidic chyme coming from the stomach. So essentially, we are creating the ideal environment to break down our finish digestion of the carbohydrates, the proteins, and now we're doing the breakdown of our fats. And so this works optimally at a slightly basic pH. And so sodium bicarbonate is going to neutralize that acid that's coming into the small intestine from the stomach. If you're loving this stuff, you can take a closer look at all the things that's happening. Of course, I didn't mention every single digestive enzyme. I hit the highlights. So this is summarized in this table 9.1. And we have the first part here, and then the second part. Okay. All right. Small intestine also has a very unique structure to it. It's small, and it has folds, and we call these folds villi. And on the folds, there's little tiny finger projections called the microvilli. So you ask yourself, why do you have a fold with little folds on it? The reason why we have folds on the lining of the small intestine is because now we've increased the surface by which we can absorb the products of digestion. You worked really hard shopping for the food, growing the food, preparing the food, cooking the food, chewing the food, digesting the food, and what we need to do in the small intestine. Hi again, my computer is out of memory, so let me just navigate over here so we can finish what we're doing. All right. Okay, so let's take a look at this unique architecture, if you will, or design of the small intestine. So if you take a cross-section of the small intestine, you're going to see that it's, oh, now my battery's running low. Well, anyway. You see that there's several layers to this intestinal lining, but there's the space we call the lumen, and then all along this membrane we see a fold. Those are the villi, and then we see little tiny projections off the villi called the microvilli. So essentially, this is going to allow us to increase the surface area of the lining of the small intestine, and we can absorb those products of digestion, and it's going to go right into the bloodstream. Now notice something interesting here. We have the capillary that's oxygen rich, we have the capillary that's oxygen poor, and we have associated with it a lymphatic vessel. So why might we have a lymphatic vessel associated with that? So we want to make sure that we are protecting ourselves from harmful microorganisms that might be coming into our bodies through the food that we're eating. Hi there, I'm just trying to get our PowerPoint back up. Here we go. Why isn't it showing me? It's recording my visual.